Welcome. In this video, we are going to take a look at problem 9 from chapter 23 of College Physics 2E by OpenStax. Okay, here's a quick rundown of the problem. We have an MRI technician who has a ring on his finger, sticks his hand in the MRI scanner, which has a magnetic field, and we need to find the induced EMF. Okay, let's start with what we know. First off, we know the magnetic field that he puts his hand into is 2.00 Teslas. Okay. We know the diameter of his ring is 2.20 centimeters. We know the elapsed time, delta t, is 0.250 seconds. And we need to find the average EMF that is induced. Okay, so for part A, let's say his ring looks like this. And then his hand is in the same, his fingers point in the same direction of the field. So let's say his hand is going into the page, then the field is also into the page. All right, so then what that allows us to say is that at the start, the magnetic flux is 0 because he has not put his hand into the magnetic field yet. At the end, the magnetic flux is B times A times the cosine of 0. And that is because the normal to the area of the loop, so the area made by his ring, the normal to that area is in the same direction as the magnetic field. And so the angle between the normal and the magnetic field is 0. And the cosine of 0 is 1. So at the end, the flux is B times A. Okay. We are also going to assume that N is equal to 1. Okay. And so we will find the magnitude of EMF. So we'll take the absolute value of both sides. So minus N, we'll replace the N with a 1. Time rate of change of flux. So the magnitude of the induced EMF is going to be the change in flux over the change in time. Okay, the change in flux is going to be the flux at the end, which is B times A, minus the flux at the start, which is 0. And then we divide by delta t. Okay, so our induced EMF is going to be the magnetic field, which is 2.00 Teslas. Then we need the area of the ring, or the area made by the ring. So we'll have pi r squared. Okay, we have a diameter of 2.20 centimeters, so we need to divide that in half to make it a radius. Then we also need to convert it to meters. And so 1 meter has 100 centimeters. And we need to square all that. Then we just need to divide by the elapsed time, which is 0.250 seconds. Okay, I did that calculation and I got an induced EMF of 0.00304 volts, which we can also call 3.04 times 10 to the minus 3 volts. Okay, so that is part A. Now in part B, we want to know if the heat if the ring heats up. Okay. And so the power dissipated by a resistor is V squared over R. Okay. And so let's assume R is about 1.00 milliohms. Okay. And then the power is going to be the EMF we just found. So the 3.04 times 10 to the minus 3 volts divided by the 1 milliohm, which we need to convert to ohms. And in 1 ohm, there's 1,000 milliohms. Okay, so I found a power of 9.24 times 10 to the minus 3 watts. So not very powerful, but the heat Q is equal to power times time. And so heat Q is going to be the 9.24 times 10 to the minus 3 watts times the 0.250 seconds. So Q ends up being 2.31 times 10 to the minus 3 joules. So no, that is not a lot of heat, and so no, him putting his hand into the MRI scanner when the field is on will not significantly change the temperature of his ring. Okay, I hope you found that helpful. Let me know if you have any questions. Thank you for watching, and I'll see you in the next one.